This video ended up a little bit longer than I expected, so I've made an index down the bottom in the YouTube description, which you can click on at any time. Hello, welcome to RCHacker. First up, thanks for all the great responses in my last video. I've really got a good idea of the direction I want to go with this channel. So thank you for all those comments, guys. Now, this video today is all about the Turnstile antenna. What I've made a couple of cheat sheets. This is one for the V antenna. I didn't announce it when I made that V antenna video, but I've made a cheat sheet for it now. You can view it on my website, a link to this, and also in the video comments. There's also one for the Turnstile antenna. Building them is pretty easy. Basically what I've got is where to solder them and a table of the measurements that you need for each frequency as well. So I'm going to put this together into a cheat sheet that you can print out and keep on your RC desk. So building these antennas, all the information you need should be here for each of the different frequencies, and that goes from about 425 megahertz up to 1280, and I've just chosen a whole lot of different frequencies based on the comments from my previous V antenna video, so you're welcome to go and check that out. Anyway, we'll move on to this video. We are doing entirely simulations, looking at simulations using the 4NSE2 software. So if you want to play along and follow, there's a antenna design sections on the DIY section of my website. And there's a link here to my GitHub repository and to the 4NSE2 software as well, which is freeware for Windows. And you can go there and you can download this repository here. I think if you just download the zip on this link, you can get access to all those files. Now, these are all the antenna designs that I've been playing with. Some of them have nothing to do with what I'm going to be talking about, so no guarantee whether any of them work or the designs are good. They're just what I've been working with. So if you want to get started, they're all related to RC stuff, so at least there's a point if you want to get started using this simulation software. Right, moving on. Let's go to my virtual machine. Computer's having a bit of a hernia at the moment. It's recording this video and doing some compiling at the same time, but anyway. Alright, so let's have a look at the Turnstile antenna. Let's have a look at one of the first models, the basic Turnstile model. So this is a picture of the actual model here. You can see it's got two long sides and one side that's a bit shorter than the other ones. This is basically at right angles. In the middle you can see it's a bit offset there. That's just because you have to model the actual feed point. Now, one long side and one short side is connected to the outer part of the coax, and one short side and one long side is connected to the inner part of the coax. That's as simple as it needs to be. And this one is flat and at right angles. Now what we'll do, we'll calculate the far field pattern. Now this one, I think at the moment, I'll just have a look at my model. This is currently for 915 megahertz. So I'll have a look at this in 3D. Calculate that model again. Generate far field pattern. Done. 3D. Now we should be able to see our radiation pattern. So I'll just zoom this out a bit. Now the basic thing to know with the Turnstile antenna is you may have seen a lot of people are thinking incorrectly that it should be mounted flat like this, but if we look at the radiation pattern, if you have your longer arms pointing up and down and your shorter arms out to the sides, the radiation pattern is sort of circular, a bit stronger to the front and rear out the z-axis here. Now, there was one article, IB Crazy made had a design up for this type of antenna, and he's saying to lay it flat on the model. While it does work, I think it's a bit incorrect. I don't think he went and looked at this 3D model. I think he just looked at this output here and said, oh yeah, that's circular. But it's actually, you're not taking into the account the other axis there. So when you look at the 3D model, you may get different results there. But a lot of people were getting good results with these mounted flat on their aircraft, and I think that's just because compared to the other antennas they were using, these are well matched. They've got a nice low SWR value, so they work pretty well. Doesn't matter what direction. Now we'll just have a look at, that's the total gain. We'll look at the horizontally polarized energy, and you can see it's almost circular in its pattern with the horizontally polarized signal there. Okay, so if you're using say a moxon that's mounted flat on your radio with this, that's a good match. Or if you've got a V antenna on your radio and this, it's also a good match. And we'll just look at the vertical gain of that. The vertical gain is a bit different. Front and rear, it's actually quite strong. So if you're going for absolute range and you're having a bit of trouble with your reception, you might turn your radio up sideways like that to try and get better reception, and then turn it back. But if you're flying along and the aircraft's at the side and you've got your antenna, then you rotating that is not going to make much difference. You want to keep your antenna so everything's polarized horizontally rather than vertically. So this antenna is better for horizontal polarization around the aircraft. If you're laying it with the long sides upwards and downwards and the short sides out to the side, then you're going to have not great reception from the top and the bottom. Hopefully you guys can see that there. Alright, so let's move on to a couple of the variations of the antenna that I wanted to show you guys. Now what I did, I got the turnstile antenna and I added the coax to the model here. Now when you've got coax on any type of antenna, the attachment point, the actual outer part of the coax acts as part of the antenna as well, and this is quite important, and you need to take this into account when you're fitting your antenna and you're designing your antenna. Now most amateur radio antennas and that sort of thing get by this problem by having what's called a balun really close to the antenna here, which stops any of the electromagnetic radiation going down that outside of the coax. So it might be through a ferrite core and a couple of turns around it or something like that. But mostly in our case, when we're dealing with RC antennas, we want to keep it light and we want to keep it simple, so we can't really do all the baluns and matching transformers and things like that. We want to keep it nice and simple. So what I'll do, I'll just show you what this the radiation pattern for this looks like. So here we've got our model laid flat, and if we add our radiation pattern here, sorry, we'll make it the multicolor one. You can see that it's because of the addition of this extra element here, it makes the shape of the radiation pattern really, really off and lumpy, and while it'll still work, it's not the the actual radiation pattern that you would expect. Now, just to show this is the same model, if I open up the model file here, and this line here, this defines the geometry of the antenna. This is just the line where I defined that actual extra bit of coax. So we'll delete that row. I'll save the model. Close that. Now we can see it doesn't have that there again, and we'll calculate our far field pattern and show the multicolor pattern, and we're back to our normal radiation pattern. You know, you can see it's slightly off at an angle there, and that's just because of the offset of the where I've modeled the actual coax feed point, because there is a little bit of a gap in there. So what are we going to do? What in our application, how are we going to mount ours? So I've got another model. Instead of everything laid flat, I'm mounting it slightly different in sort of I call it a flower configuration. Okay, so we've got our model here, and this is our coax going out one side. Could be the base. And I guess the best way to mount this type of antenna would be with the top and bottom, the longer arms going top and bottom, and then these two out to the side, and just say it's sticking out on one arm of the multi-rotor, or in the case that I did, out the back of the rudder on the Raptor. But I'll show you that a bit later. Now, if we look at the 3D model for this one, hopefully the model is all ready and calculated. No, it's not. That's because I've done a frequency sweep. It only shows actually one part of the antenna. So we'll just do a far field pattern again, calculate that. I'm going to change my rotational element to the number 1 element. That just makes it so it rotates around the center, and then we'll show our multicolor. So you can see that with the coax coming out from the middle, it doesn't actually affect the radiation pattern that much at all. It's just to do with symmetry, I guess, and same reason why your pinwheel antennas, well, your cloverleaf antennas, if you've got your coax going down the bottom, it doesn't really affect the radiation pattern that much because it's to do with symmetry. This antenna works the same way. I'll just zoom that out. So you can see the radiation pattern there. Strong out the front and out the back, and you know, still reasonably strong out the sides, but top and bottom not that great. Now I kind of like it strong out the front and back, because you could imagine you're flying away from yourself, you've got good reception, and then you turn around and come back towards yourself and you've still got good reception. And I guess along the way you could do turns and stuff, and you can notice if it's getting weaker or not, and if in doubt you just head back towards yourself and you know you're getting the best reception for that antenna. Right, let's have a look at another one. I'll quickly show a bit of footage of the antenna that I actually built to use on my Raptor. On the Turnstile antenna. Let's pull that out there. This goes out the back of the plane. This is sort of it's a turnstile with a bit of an angle, and I've had the testing was good so far. Now this one had a bit of an angle to it. I made the model a bit more complex and I put an angle on here. This isn't in the cheat sheet. It improved the It improved the SWR performance of the antenna just slightly, and it also gave it a bit more of a stronger signal out to one side of it. In this case, I think it was out to the rear. No, this is pretty much symmetrical. So this was like, this one worked out really well. It was actually stronger all the way around the sides and a bit weaker top and bottom. And that was by putting that a little bit of an angle there. This isn't in the cheat sheet. It's a bit of overkill. If you really want to go this far, you should be getting involved in using the actual antenna, this software anyway. But the models are there for you to have a look at. And then I added one with the coax as well. It's just so we can have a look at the model of that. It did warp the shape of it a little bit, but it was still pretty usable. And then I also, let's just zoom that out a bit so you can see that. And then I also had one where I actually modeled, which one was it? Yeah, this one will do. So what I've done here, this is what I put on I've put on my Raptor aircraft, and I've modeled the coax going from, you know, midway in the fuselage and then up the actual rudder, and then out the back, and that's where the antenna is mounted out the back. And these extra ones here are the actual control lines, because they are metal control lines. And if you really want to be accurate when you're modeling your antenna, you need to model the parts of the aircraft that are made of metal as well. So that's really important. And that's why if you're putting this antenna and you wanted to get maximum performance, say on a multi-rotor, you'd want to stick it out on one of the arms, like out the back of the multi-rotor, so it's well away from all the metal wires that you know, connect the motors and the ESCs and all that sort of stuff, because that will affect your radiation patterns. And let's just turn on the radiation pattern here. So this is what I ended up with the model on a Raptor. Let me just change that rotation center, and we'll just zoom that out so I can see the antenna structure. So what happened here, all this extra stuff on the front did affect the radiation pattern, and it actually made it so it would get a stronger signal out towards the front, which is kind of counterintuitive, but there you go. That's what the modeling software says. And then out the back, it's a little bit weaker. So and top and bottom, the signal is actually a bit weaker as well. But I went with this because when I turn around, I know I'm going to get the stronger signal, which is, for me, quite desirable. So if I'm starting to lose packets as I'm flying along, if I'm doing distance or something like that, all I have to do is fly back towards home and I'll get my strongest signal again, and I should be in control. Okay, so that's the Turnstile antenna. Honestly, when I started out with it and I started modeling with it, the radiation pattern wasn't as I expected. If you look at, if you just do a Google image search for the Turnstile antenna and have a look at some of the images there, you can see why there was a bit of confusion as to the correct orientation of these antennas. Like here, they have the Turnstile, but they're mounted two, one on top of each other, and that creates an entirely different style of antenna, changes the radiation pattern and everything. And also, if you have this type of antenna and you've got a big ground plane as well, it will also change the performance as well quite a bit. See, this one's starting to look like a pinwheel antenna. It's one of the RC Cam articles with the way not to mount that coax, because it makes a big difference, although it does have a little balloon there. How effective that is, not really sure. There's another RC version, and here's another one with the extra elements in here. Here's an amateur one that's mounted, and he's actually mounted it vertically there as well. So this way, may not be correct. You'll get good, you know, it's nice, it's out of the way and everything like that, but you need to take into account other bits of metal, like this this control rod with this servo here will affect the performance of this antenna as well. Okay, some other characteristics of the Turnstile antenna worth mentioning. So let's just go back to one of our base models here. Now this is one for 433 megahertz, and what I'm going to calculate a frequency sweep. So we're going to go see what the performance of this antenna is like from 400 to 500 megahertz. And this software is amazing. It does lots and lots and lots of maths. And back in the day when it was designed, it was all designed just on command line software. So it would take text files and it was entirely command line. All this is just a GUI that is thrown on top of the existing command line programs, and they're really old and well proven. And it does lots of calculations. So we're testing this antenna from lots of different angles and lots of different frequencies at the moment. And when that's done, we should have a nice graph. Here we go. So what we've got here, this is the SWR here for the antenna, and this is the frequency along the bottom here. And this particular one, you know, it's best at 433 megahertz, which is what we designed it for. And it's also pretty good at 460 megahertz up here. This is just complete coincidence. But, you know, you could probably use this antenna equally well for 459, which is what the UK guys use their antennas, need to use their open LRS gear at to be legal. So you got 433 there, and then there's another point where it's actually good performance at 459. Anywhere in between that, the results are pretty good. The reflection coefficient goes up a little bit here, so you are going to get slightly worse here, but you could also hop across these frequencies as well, and this style of antenna will work quite well. You've got to think also the performance of your other antenna at the other end, whether it's a V antenna or your moxon antenna, and see what your actual performance here is like. Let's do that. Let's go. Let's check out. I think I've got a moxon here. 435 as per the generator. Let's load that one, and we'll do output data, and we'll do a frequency sweep. The model for this one is actually a bit simpler. It's got less elements in the model, so the calculations happen a bit quicker. And we'll look at our graph here. So you can see the moxon antenna is quite a narrow band antenna. It's got a frequency where it performs the best, and in that case it's here at about 435 megahertz, and like this antenna would not work well at 459, for instance. The SWR is going to be going up to 2, and your reflection coefficient has gone up as well. This is another measure of the performance of the antenna. So that's a bit more narrow band, and then we'll have a look at, just to complete it all, we'll have a look at the V antenna. Well, let's have a look at the V antenna with the coax on it. Okay. Oops. Frequency sweep 400 to 500. There we go, and we can have a look at our graph, and the V antenna is also relatively narrow band as well. So what this means is with the V and the moxon, if you're going to use them, they're simpler designs in a lot of way. The moxon is a good directional antenna, but you need to be quite precise with your measurements as well with these two antennas. If you've got elements slightly longer or a slight angle off or anything like that, they're going to deviate from this center frequency, and then they'll come out of tune a bit more rapidly. And while our turnstile antenna, is that the one we were using? While our turnstile antenna is a very broadband antenna, so you can design it for a specific frequency. We were designing, or I was doing my designing, so it would be in this null here, and you know that you've got actually a fair bit of leeway. In this case, lots more leeway above than below, but you've also, because of this wideband characteristic, you can be a little bit more inaccurate with your measurements as well. But it's not a problem to be down to a millimeter anyway. The values that I've got on my actual cheat sheet here, they're accurate to a millimeter, which is more than enough. 2 millimeters is fine. Right, one last thing while we're here with the software, what I was going to show you, I'll just show you how I actually came up with those values in this on my cheat sheet here. So I had my base antenna design, and I've got my model here, and in the model, a model's got not a huge amount of mathematics in it, but it's got labels and what you might call variables if you're programming. It's sort of a spreadsheet, mini programming language in its own way. But here I've got south, north, east, west. East and west are the short elements, south and north are the long elements, and then I've got actual values for short and long. In this case it's 70.4 and 80.1. And up the top we have our frequency. So this is for 915. What we'll do, we'll change the frequency to 440 and then we'll save it. Now this is a huge step to go from 440 to 915. I'll also change the radius of the wire because I'm using 0.88 for the bigger stuff, so we'll save that. And my feed element was defined as 2 millimeters as well, so I'll do that just so we're consistent with the stuff that I've actually already calculated, and I'll save that model. You can see that sort of thing might change a bit there. I've done this, that's quite big. I could actually make it a bit smaller, but you're going to get those sort of discrepancies when you actually make it with your coaxial feed point. There is going to be a bit of a gap there. Anyway, so then we go to this option here. We start our optimizer. And this is where this software gets really cool. So we take our short element, 70.4, and our long element, and we'll select those two as our variables that we want to change. And up here we've got our weighting factors for what type of antenna performance we want to actually design to. There's a whole lot here. You've got just straight SWR. Currently by default we want to go for the best SWR possible. You've got gain, so you might want to go, there's a right click for options. So you might want to maximize your gain, or you might want to minimize your gain. You might want to set a target gain for your antenna, or you might want to make it good enough. So I didn't realize that. There you go. I've just learnt something new with this software just because I had that mouse hovering there. So there's different settings you can do for that. If you're going for a directional antenna, you might want to set the gain. If you want to go for absolute range, you might want to set this gain here to 100% and reduce the SWR. You want the SWR as a factor as well. There's also a few other R in and X in is basically related to SWR, is the impedance in our target is 50 ohms, which is 50 here and 0 here. And then our efficiency, I think that's just the efficiency of the antenna as a whole. I have designed antennas using the efficiency as well, and you get slightly different results, slightly different radiation patterns and things like that. Something you might want to play around with. Anyway, so we've got 440, and we'll just leave it at SWR. And when we click go, what it's going to do, it's going to vary. It makes small variations to the short and long variables, and then does a calculation on the SWR here. And I think, I turn off that 3D model, you can actually see it. Oh, it's a bit bigger. You can actually see it making it's not letting me zoom out at the moment because it's busy. But if this is correctly scaled when you first start off, it'll let you see the actual variations here. So we'll just let that go. I'll fast forward it. Sometimes it can sort of get stuck in its own little loop, stuck around a certain value, and then it just keeps going and going, never really improves itself. But there is a bit of an algorithm going on here. It makes a small adjustment, sees if the SWR is better, and then makes another adjustment. If it's worse, it makes an adjustment back the other way. So it does all that sort of thing automatically. So it sort of basically does tries out lots and lots of calculations and evolves it, evolves the antenna so it gets better. So I'll just let that go. Okay, so it says it's optimized. We've got an SWR of 1.08, which is pretty low, and that was run number 27-2, and we've got 141 millimeters and 163, which is a bit shorter than the calculation that I ended up on my cheat sheet. So what I'll do, I'll just run that again and we'll see if it goes a bit closer. Now, I normally like to run it a couple of extra times just to make sure that it settles in the right spot. And that's what I did with all the ones on here. But what I've actually got a slightly different result to what I expected. Now, why is that? So on my cheat sheet for 440, I said I had 146 and 166, and here I've got 141 and 164. So what I'll do, I'll update the NEC file, and I'll just call it new for now. And we'll just do a frequency sweep on this. I got a feeling this is on the other null. It's optimized itself and ended up on the actual other null. No! We've actually come up with a turnstile antenna design which is not quite as broadband as perhaps the one that I've got here on the cheat sheet. It's actually got this quite defined spot here. So I'll just go back to the model. What you can do, you can actually manually adjust it as well. So I'll do what I've got in the cheat sheet. I've got 146 in there, and then 166, and I'll save that, and then still frequency sweep for that, and see what we get. Okay, so this antenna is becoming quite narrowband, this actual iteration for the number 440. Let's just check. That's for 440, 146. So let's go to 433, which was 150, and 170. You know, I think I've said all I wanted to say on this video. Now, you know, just follow along to see how I think when I'm using this software. So I'll just run that output data again. Now, when I made that graph, I was very methodical about it, and I was pretty happy with the results. But it just goes to show that even though I did all this optimization, the characteristics of each antenna varies a bit. Again, it's quite narrowband. So that's fine. That's normal. Now, when I did that graph before, so the actual act of, alright, so I've just learned something else again as well. All that stuff about these antennas being quite broadband is only really comes into effect when you've got this, you take into account the coax on the back there as well, which is really interesting. So you can have a lot of, I find this really interesting, like you will get, if you get into the software and you start getting your head around how it actually works and what it's doing, it can be actually quite addictive, because you'll do small changes and that sort of thing, and you'll try and figure out, oh, that sort of works better, and then you'll go in that direction, and then you'll make stuff. And I was I got on the IRC network with the OpenLRS guys, and there's a couple of guys have been playing around with antenna designs as well, and we've been throwing them back and forth. It gets really, really interesting. So if we have our antenna with this coax on the end, it becomes a little bit more broadband. Of course, you're not going to get the antenna without the coax on the end, so you're going to get this characteristic, which is good. Anyway, I've done a whole lot of calculations. If you don't want to mess around with the software and you just want to build the antenna, go with these. They should work pretty well. Keep in mind, I haven't actually gone out and tried these and actually done all the testing and all that sort of stuff. So there's no substitute for actually testing these antennas in the field and doing a bit of experimentation. Okay, there still may be other factors that we're not taking into account. Velocity factor is one. Shouldn't really affect it too much, but they are factors that you should think about, and the thickness of the wire and stuff like that. I'll put some notes on the thickness of the wire on the cheat sheet as well, so you can have a look at that. There'll be links below in my video to the cheat sheet and the other antenna videos. There's also an antenna playlist as well, so please have a look at that. And if you haven't seen my new channel, Biodiversity Shorts, please have a look at it if you're interested in nature documentaries, David Attenborough style nature documentaries. It's going to be my own style, but I like filming wildlife, and I thought I'd make a new channel out of that, particularly since FPV has become illegal. Well, almost, we hope not, but they're practically trying to make FPV illegal in the States, which is really, really disappointing. Flight test, and I think Bruce had something to say on that. If you're from the States, there are various petitions which you can actually sign to try and get people to do something about it. I feel bad for you guys. It seems like your country's going a bit to pot. Fun police are out in force. Anyway, I don't have to worry about that. I'm out here in Ecuador, and I don't think anyone really knows what it is. There's probably only 1 or 2 people actually doing FPV in the whole country. I think that's me and Colorex. So we sort of lay low, and we're not a problem. I'm out in the jungle anyway. It's not an issue. Anyway, cheers. Thanks for watching. I will catch you next time. If you've got any comments or questions or anything like that, or if you think I've made any mistakes in this video, please discuss in the comments below. I do read everything. Cheers.